To help me explain these concepts, I made up a situation in which I'm a researcher who's interested in estimating the mean age of a population of 24,000 people. Unknown to me, the mean age of this population is 24, with a standard deviation of 8. Remember that mu is a symbol for population mean, and sigma is a symbol for population standard deviation. So the population mean is 24, and the population standard deviation is 8. Let's think about what these two numbers are telling us. I think that the mean is the easier number to understand. The mean is just telling us that in this population, the average age is 24. The standard deviation is a little bit more challenging to understand. What the standard deviation is telling us is that in this population, the average distance to the mean of 24 is roughly 8. In other words, if you looked at all of the people in this population, most of the people would fall somewhere between 16 years old and 32 years old. Let's say that I decide to randomly select 4 people from this population. I decide to randomly select 4 people, record their ages, and then calculate the mean of those 4 ages to estimate the mean age of the population. I know that 4 seems like a pretty small sample size, but we'll just use 4 in this example. In order to get an idea of how accurate my sample mean is likely to be, I decide to calculate the standard error in my study. Since the population size is more than 20 times larger than my sample size, I can use the short standard error formula. The short standard error formula says to divide the population standard deviation by the square root of the sample size. Remember that little n is a symbol for sample size. I'm going to divide the population standard deviation of 8 by the square root of 4, which is my sample size, and then that'll give me my standard error. The square root of 4 is 2, so I'm just going to be dividing 8 by 2. 8 divided by 2 equals 4, so my standard error is 4. Let's think about what this number is telling me. This number is telling me that when I randomly select my sample of 4 people from the population, my sample mean is likely to be about 4 away from the population mean. In other words, my sample mean is likely to be about 4 off target. Now this standard error isn't telling me that my sample mean is definitely going to be 4 off target. It's just telling me that my sample mean is likely to be about 4 off target. The exact amount that my sample mean is off target by depends on which sample I end up selecting. You might be wondering how I would calculate the standard error in my study if I don't know what the population standard deviation equals. We'll actually talk about that situation in a different video. We'll talk about how a researcher who doesn't know what the population standard deviation equals will use a slightly different formula to calculate a value called an estimated standard error. However, in this video, we'll just pretend that I do know what the population standard deviation equals and that I can calculate the actual standard error. Now that we have reviewed the concept of the standard error, I'd like to go over the z-score of a sample mean. Let's look at the numbers on this number line and find the z-scores of some of these numbers. First, we have to realize that when the sample mean equals the population mean, the sample mean has a z-score of 0. In my example, the population has a mean of 24, so if my sample mean comes out to 24, then my sample mean will have a z-score of 0. If my sample mean comes out 1 standard error below the population mean, then my sample mean will have a z-score of -1. And if my sample mean comes out 1 standard error above the population mean, then my sample mean will have a z-score of +1. In other words, if in my example, the standard error is 4, so if my sample mean comes out 4 below the population mean of 24, then my sample mean, in my example, the standard error is 4, so if my sample mean comes out 4 below the population mean of 24, then my sample mean has a z-score of -1. If my sample mean comes out 4 above the population mean of 24, then my sample mean has a z-score of +1. In other words, if my sample mean comes out to 20, then my sample mean has a z-score of -1. And if my sample mean comes out to 28, then my sample mean has a z-score of +1. If my If my sample mean comes out 2 standard errors below the population mean, then my sample mean has a z-score of -2, and if my sample mean comes out 2 standard errors above the population mean, then my sample mean has a z-score of +2. In my example, the standard error is 4, so if my sample mean comes out 8 below the population mean, then my sample mean has a z-score of -2, and if my sample mean comes out 8 above the population mean, then my sample mean has a z-score of +2. In other words, if my sample mean comes out to 16, then my sample mean has a z-score of -2, and if my sample mean comes out to 32, then my sample mean has a z-score of +2. At this point, let's actually take a random sample of 4 people from the population. Once we take our sample of 4 people, we're going to record the ages of the 4 people in the sample, calculate the mean of the sample, and then find out what the z-score equals. Let's say that we randomly selected these 4 people to be our sample. I decided to give each person in the sample an ID number, and these are the ages of the 4 people in our sample. The mean age of this sample is 22. If you added these 4 ages and divided the total by 4, the answer would be 22. So x bar is 22. Remember that x bar is a symbol for sample mean. I put an x bar up here on the number line just so you could see how close our sample mean is to the population mean of 24. Let's see if we can figure out the z-score of our sample mean. There's a formula that can be used to calculate the z-score of a sample mean, but I want us to try to figure out the z-score just by looking at the number line. We can see that 24 has a z-score of 0, and 20 has a z-score of -1. 22 is about halfway between those two numbers, so 22 has a z-score of -0.5. Our sample mean of 22 has a z-score of -0.5. Let's double check that answer using the z-score formula. We're going to take this sample mean of 22 and plug it into the z-score formula, and then we'll see that the z-score really is -0.5. This is the formula for the z-score of a sample mean. The z-score formula for a sample mean says to subtract the sample mean by the population mean, and then divide by the population standard deviation over the square root of the sample size. So I plugged in all 4 numbers. I plugged in our sample mean of 22, the population mean of 24, the population standard deviation of 8, and the sample size of 4. If we did the math, we would see that the z-score does come out to -0.5. So our sample mean of 22 does have a z-score of -0.5. Let's do this again with a different sample. I'm going to repeat my study and randomly select a new group of 4 people from the population. Just like last time, I'm going to record the ages of the 4 people and calculate the mean age of my sample to estimate the mean age of the population. This time, I selected these 4 people to be my sample. I changed their ID numbers so you could see that this is a different sample of 4 people. Even though person 173 was in the first sample, I decided to include this person in the second sample as well. I did that to show you that it's possible to select a person more than once when you do random sampling. If you're sampling from a large population, that's really unlikely to happen, but it can happen. Over here, I recorded each person's age. The mean of this sample is 24. If you added these 4 ages and divided the total by 4, the answer would be 26. So x bar is 26. Just by looking at the number line, we can see that our sample mean of 26 has a z-score of plus 0.5. +24 has a z-score of 0, 28 has a z-score of +1, and 26 is halfway between those two numbers. So we know that our sample mean of 26 has a z-score of positive 0.5. Just like last time, let's use the z-score formula to make sure that the z-score is correct. This time, we're going to plug our sample mean of 26 into the formula. these other three numbers will all stay the same because the population mean is still 24, the population standard deviation is still 8, and the sample size is still 4. If we did this math right here, the answer would come out to 0.5. So our sample mean of 26 does have a z-score of 0.5. I want to stop for a moment to make sure that you notice something on the screen. Our first sample mean was below the population mean, so it had a negative z-score. Our second sample mean was above the population mean, so it had a positive z-score. A sample mean below the population mean always has a negative z-score, and a sample mean above the population mean always has a positive z-score. I want to do a couple more of these examples with you just to show you how the z-score won't always come out to a nice number like negative 0.5 or 0.5. Let's say that I randomly select a third sample of 4 people, and I get these 4 people as my sample. This sample has a sample mean of 18.5. If you added these 4 ages and divided the total by 4, the answer would be 18.5. By looking at this number line, we can see that 18.5 is about halfway between 16 and 20. That means that our sample mean of 18.5 should have a z-score of about negative 1.5 or negative 1.5. However, our z-score won't be exactly negative 1.5 because this sample mean isn't exactly halfway between the two numbers. However, we can see that our sample mean will have a z-score close to negative 1.5. It would be too difficult for us to find out exactly what the z-score of this sample mean equals just by looking at the number line. So let's use the formula to get the z-score. We're going to plug our sample mean of 18.5 into the formula, and then these 3 numbers are still the same that they were before because the population mean is still 24, the population standard deviation is still 8, and our sample size is still 4. The formula says that our sample mean of 18.5 has a z-score of negative 1.375. And this z-score is pretty close to negative 1.5. And that makes sense because our sample mean is about halfway between 16 and 20. Let's select just one more sample of 4 people. So I'm going to repeat my study a 4th time with a new sample. This sample has a mean of 31.5. If you added these 4 ages and divided the total by 4, the answer would be 31.5. 31.5 is about halfway between 28 and 32, so our sample mean of 31.5 should have a z-score close to 1.5. Our sample mean won't have a z-score of exactly 1.5 because our sample mean isn't exactly halfway between 28 and 32, but our sample mean will have a z-score close to 1.5. Let's use the z-score formula to find out what the z-score of this sample mean equals exactly. So we're going to plug in our sample mean of 31.5 into the formula, and these 3 numbers will stay the same. And the formula says that our sample mean has a z-score of negative 1.875, which is somewhat close to 1.5. At this point, I want you to notice 2 things on the screen. First, just like before, I want you to notice that a sample mean below the population mean will have a negative z-score, and a sample mean above the population mean will have a positive z-score. Second, I want you to notice how a sample mean further below the population mean will have a bigger negative z-score, and a sample mean further above the population mean will have a bigger positive z-score. Overall, a z-score shows 2 things about the mean of a sample. First, it shows whether the sample mean is below or above the population mean. At this point, I want you to notice two things on the screen. First, just like before, I want you to notice how a sample mean below the population mean will have a negative z-score, and a sample mean above the population mean will have a positive z-score. Second, I want you to notice how a sample mean further below the population mean will have a bigger negative z-score, and a sample mean further above the population mean will have a bigger positive z-score. Overall, a z-score shows two things about the mean of a sample. First, it shows whether the sample mean is below or above the population mean. Second, it shows how far the sample mean is from the population mean. When a sample is selected from the population mean, at this point, I want you to notice two things on the screen. First, just like before, I want you to notice how a sample mean below the population mean has a negative z-score, and a sample mean above the population mean has a positive z-score. Second, I want you to notice how a sample mean further below the population mean will have a bigger negative z-score, and a sample mean further above the population mean will have a bigger positive z-score. At this point, I want you to notice two things on the screen. First, just like before, I want you to notice how a sample mean below the population mean will have a negative z-score, and a sample mean above the population mean will have a positive z-score. Second, I want you to notice how a sample mean further below the population mean will have a bigger negative z-score, and a sample mean further above the population mean will have a bigger positive z-score. Overall, a z-score shows two things about the mean of a sample. First, it shows whether the sample mean is below or above the population mean. Second, it shows how far the sample mean is from the population mean. When a sample is selected from a population, the further the sample mean is from the population mean, the bigger the z-score will be. You can think of the z-score as measuring how extreme or off target the sample mean is. One thing I should mention at this point is that a researcher who is calculating a sample mean to estimate a population mean typically can't calculate the z-score of his or her sample. That's because the researcher doesn't have enough information to be able to calculate the z-score. In order to calculate the z-score of your sample mean, you have to know what the mean and standard deviation of the entire population equal, because those two values go into the formula for the z-score. The mean and standard deviation of the population are almost always unknown. To calculate them, the researcher would have to have data from all members of the population. Even though a researcher typically can't calculate the z-score of his or her sample, the z-score is still an important concept. We'll see why it's important later in this video. Now that we've reviewed z-scores, let's review the central limit theorem. The central limit theorem allows us to predict the shape of the sampling distribution. The central limit theorem says that when the population that's being sampled is normal, the sampling distribution will always be normal. And when the population being sampled is not normal, the sampling distribution will be roughly normal with a sample size of 30 or larger. In this example, I'm taking my sample of 4 people from a normal population, so my sampling distribution will be normal, even though I'm only selecting 4 people to be in my sample. When you're randomly selecting a sample from a normal population, the sampling distribution is always normal, no matter what the sample size is. This normal curve is showing my sampling distribution. It's showing all of the possible outcomes that I could end up getting in my study. In other words, it's showing the means of all possible samples of 4 people that I could select from this population when I do my random sampling of 4 people. Each time I randomly select a sample of 4 people from this population, and I calculate the mean of my sample mean is one of the sample means under this curve. For example, my first sample had a mean of 22, so that sample mean was one of the sample means over here. My second sample had a sample mean of 26, so that sample mean was one of the sample means over here. My third sample had a mean of 18.5, so that sample mean was one of the sample means over here. And my fourth sample had a sample mean of 31.5, So that sample mean was one of the sample means over here. Now that we've reviewed the idea of the central limit theorem, we can move on to discuss the margin of error. Let's start with the definition of the margin of error. The margin of error is the distance from the population mean to the lower and upper boundaries of a certain percentage of the sampling distribution. This definition might not seem clear right now, but it should be clear after we go through a few examples. We'll go through a few examples of calculating the margin of error, but before we do that, I wanted to go through a quick exercise to help us understand the definition of the margin of error. I want you to imagine an area under this curve that includes the middle 60% of the possible samples. I want you to imagine that that area has a lower boundary and an upper boundary. 20% of the possible samples are below the lower boundary, and 20% of the possible samples are above the upper boundary, and the middle 60% of the possible samples are between the two boundaries. So we have a 20% area, a 60% area, and a 20% area. Since this sampling distribution is normal, the distance from the population mean to the lower boundary of the middle 60% and the upper boundary of the middle 60% would be the same distance, and that distance would be called the 60% margin of error. The 60% margin of error is just the distance from the population mean to the lower boundary and the upper boundary of the middle 60% of the possible samples. Now I want you to imagine an area under this curve that includes the middle 80% of the possible samples. I want you to imagine that that area also has a lower boundary and an upper boundary. 10% of the possible samples are below the lower boundary, 10% of the possible samples are above the upper boundary, and the middle 80% of the possible samples are between the two boundaries. So we have a 10% area, a 10% area, and an 80% area. Once again, since the sampling distribution is normal, the distance from the population mean to the lower boundary and the distance from the population mean to the upper boundary will be the same distance. In this case, that distance would be called the 80% margin of error. The 80% margin of error is the distance from the population mean to the lower boundary and the upper boundary of the middle 80% of the possible samples. There's actually a different margin of error for every percentage. For example, the 50% margin of error is the distance from the population mean to the lower boundary and the middle boundary of the middle 50% of the possible samples. The 85% margin of error is the distance from the population mean to the lower boundary and the upper boundary of the middle 85% of the possible samples. There's actually a formula that can be used to calculate the margin of error for any percentage. I'll show you that formula in just a second. First, I want to mention that the margin of error formula can only be used when the sampling distribution is normal, like it is on the screen right here. There are three situations in which the sampling distribution is normal and the margin of error formula can be used. The first situation is taking a small sample of less than 30 from a normal population, which is what I'm doing. The second situation is taking a large sample of 30 or more from a normal population. And the third situation is taking a large sample of 30 or more from a skewed population. Actually, the only situation in which the margin of error formula can't be used is taking a small sample of less than 30 from a skewed population. In that situation, the sampling distribution isn't normal, so the margin of error formula can't be used. This is the formula for the margin of error. It actually has two parts to it. This part is just the standard error. It's the same formula we have over here. It's the standard deviation of the population divided by the square root of the sample size. This part right here is called the confidence coefficient. It has to be looked up in a table. When I go to that table, I have to actually look up the confidence coefficient that goes along with the percentage that I'm using. For example, if I want to calculate the 60% margin of error, then I have to look up the correct confidence coefficient for the 60% margin of error. If I want to calculate the 70% margin of error, I have to look up the correct confidence coefficient for the 70% margin of error. There's a different confidence coefficient for every percentage, and I just have to look up the correct one for the margin of error that I want to calculate. I think this will all make sense once we go through a few examples of actually calculating the margin of error. For our first example, let's calculate the 70% margin of error. The first step would be to go to the table and look up the correct confidence coefficient. We would need to go to the table and look up the confidence coefficient for the 70% margin of error. If we went to that table, the table would tell us that the confidence coefficient that we need to use is 1.04.